All right, SCH503 students, um, welcome back to this session in which we'll be talking about equilibrium, the pH, and another unit you're going to be calling pKa. Perhaps you've just heard about the, the pKa, but there is a common sign here, P, and then the P here. So later you're just going to see, just like a mathematical notation, that this P is just like a mathematical notation of where you've got the negative uh, logarithm to base 10 of the concentration of the hydrogen ion. Yeah, yeah. So what you're going to see is that the logarithm scale has been a good way of just illustrating uh, uh, good numbers. Yeah, I mean big numbers. For example, you may just see something like the earthquake, the shaking, or the tremor. Is usually measured like in Rich, Richter scale, as it's called, like that one. So, so you can see something like uh, there is Richter scale 1 up to the most extreme one of 10. This is a logarithm scale, yeah. And but the actual tremor, for example, like between 5 and 6, is really like is it like 10 or so there's that logarithm scale, yeah, between one to the other one. So it's like is it like 10 times, yeah, logarithm scale, maybe from one unit to another one. Yeah. So just like also with the cars, you're going to see it being said like the engine is 2.0, just, but in the normal one is just 2000 cc. Somebody may want may find it easier to say 2.0 or 1.5 as opposed to 1500. Yeah. Uh, so the logarithm scale is much uh, easier uh, to talk about. So in this case, you're going to see the hydrogen ion concentrations can be in very large numbers. It can even be in 100,000s or even in millions. Uh, and and what you're just going to see is that hydrogen ion concentration, especially for big, for large, I mean for strong acids, is very large and positive. So, but you're just going to be, if you're just going to get a logarithm of a positive number, then you're going to get it being something like maybe 506. That's like 10 to power 506. But what you're going to see is that there are very few acids which are going to be strong, but most of the other organic compounds have got very small hydrogen ion concentration. So let's see, to be able to take care of the majority of the organic compounds which have got very small hydrogen ion concentrations, so usually get a negative, so that for those small ones, instead of quoting always negative, 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 if you're going to get a negative and then the logarithm of that, then you're going to get a positive figure, yeah, something like that, yeah. So that you're going to see the same thing about the Ka, yeah. Ka is the ionization constant. Um, so there is the equilibrium constant, which you can see sometimes be called Kc or equilibrium constant, and it's the concentration of the products. Concentration of the products. The product can be more than one, yeah. Concentration of the products over the concentration of the reactants. So naturally, it follows that if the concentration of the products is is greater than the reactants, then the equilibrium constant, KCO, I can put equilibrium constant, will be greater than one. Similarly, if the concentration of the products is less than the one for the reactants, then the equilibrium constant will be less than one. This is normally true for weak acids, in which the parent compound does not ionize fully. But for strong acids, then you're going to say it's going to be fully ionized. For example, if you're going to get hydrochloric, sulfuric acid, nitric acid, they usually fully ionized like in water. So the concentration of the product, which will be H plus plus the anion, they're going to be much higher than, in fact, they will be very negligible of the starting material. So the denominator will be very large for, will be very small for strong acids. But for weak acids, then the denominator will be large. So it will be large and it will be large. So that will make the concentration of the reactants to be very small. So you're going to get a 10 to the power minus something. So if you're going to get log base 10 of that, you're going to get a negative figure. And if you're going to put a negative log, you're going to get a positive figure, something like that. Yeah. So that's the reason why there is this negative log base 10 of that one. But just to know that that the ionization of a substance in water, okay, can you see this notation? Ha means A is the anion, and then H is the proton anion. So that if I'm having like a HCl, in this case, H is your proton, and then the A minus is Cl. Yeah, can you see that? So A is the anion. If you're talking about sulfuric acid, then the A is hydrogen sulfate. Yeah, something like that. All right. So in this case, you're going to have this one ionizing to give H plus plus anion. But as you know, these are ionic substances, and they usually stabilize if you've got a polar solvent. In this case, it's going to be water. So you need to show your substance which is ionizing to ionize in a polar solvent. In this case, it is water. So if they are going to, if it's going to ionize, I'm showing an equilibrium constant. Yeah. In this case, I'm just saying there's an equilibrium there. But later, I think I'll refer you to another book which I think I've downloaded, which I've uploaded onto the Google Docs. The one which I put on the Google Docs is the modern version of this book. It's called can you see? It's called Electron Flow in Organic Chemistry. It's by Paul H. Scudder. It's to me, it's by far the most. It's to me, it is the best book on mechanism you can ever get around the world. Yeah, others they're just showing mechanism, but this is by far. Uh, uh, to me, it's best. In addition to showing various mechanisms, it's just going to be showing you, hey, this is how you're going to have orbitals interacting. If you're going to have, anions or cations, it's just going to be showing the full number of lone pairs around, as opposed to just the others just assuming something like the rest, and so many things in addition to finding about what do you call it? The 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 IUPAC nomenclature for the mechanism. Did you know that mechanisms have got IUPAC nomenclature? So they are called by the proper nomenclature. The others will just be mentioning mechanism, but this one will tell you this is the proper IUPAC nomenclature for this type of mechanisms. You'll be surprised by that, but mechanisms have an IUPAC name. Yeah. Okay. Good. So this book, this is the one which I've got, but later there was one which came after that. Though there are some revisions, there are some data which has been revised from the time this the version I had came out, and therefore, but I'll be able to mention some of the things which uh, uh, which are based on this book, which have been revised, especially on one equation. It's a bit critical, and it's going to tell you something about the direction of the equilibrium arrow. Why am I mentioning this? In this case here, just going to show this just like an equilibrium. Yeah. In this case, you can say the products can equilibrate to the certain materials, and the certain materials can equilibrate to the products. if you're going to read from this book, in the place we are going to show, you're going to say, hey, you may be thinking you're going to have an equilibrium, but if the concentration or if the equilibrium constant will be in a certain range, then you're either going to have a forward arrow, meaning that the reaction will be irreversible, or it can be backward in case the concentration of the product is much less than the one for the starting material. It means that the concentrations uh, for the reactants are much greater than the one for the product. So for all practical purposes, that reaction is cannot move forward. So you're going to say, hey, there's a forward arrow, then you're going to say an X. So therefore, that reaction cannot move forward. Or sometimes you can have the concentrations of the products being greater than the one for the reactants. So you're going to have an equilibrium arrow in which the top arrow will be much greater than the one for the reverse. So you're going to come to different arrows which you can show. In this case, you just say the concentration of the product and the reactions are the same. So you're going to have an equilibrium constant of 1. But that is not always the case, yeah? So keep note of that one. And all that information you can get from this book. It's called the Electron Flow in Organic Chemistry. To me, it's by far the world-best book on mechanism. And if you're going to ensure you really understand the different examples and the illustrations in this book, you'll never get wrong with mechanisms. Personally, when I was doing my postgraduate, I was introduced to this book, and until now, that was around it's sometime back in 1993, and I've never regretted. Yeah, it's been a it's been a it's a very good book. Yeah. So the equilibrium constant is the concentration. In this case, if uh, okay, in this case, the equilibrium constant is the concentration of the products over the reactants. In this case, if you're going to use water or any other solvent, normally the concentration of the solvent is far much greater than the one which you are dissolving. So normally the concentration of the solvent, which in this case is water, does not change. So the scientists have just done will be to remove this concentration of the solvent, which is water, and then they put on this side along with the equilibrium constant, and then they come with a new constant which you are going to call Ka, which is the ionization constant, which is given by the concentration of in this case, the protonated water, the anion over the concentration of the starting acid. Once again, as I mentioned, for strong acids, if they are put in water, they're going to be fully ionized. So the concentration of the Ha, which is the parent acid, is going to be almost negligible. So the Ka will be large and positive. Large and positive. But for most of the acids or most of the compounds that donate electrons, they do not fully ionize in water. In fact, it's only a small quantity of it. So normally the concentration of the product is normally much less than the parent acid. Yeah. So this is now where this one becomes useful. As I mentioned, this one minus log base 10 of the concentration of the hydrogen ion, which is uh, hydrogen ion is given the name of pH, which is the unit you are very much aware or you are familiar with, and the pH starts from 0 for the very strong acids, 7 for pure distilled water, which uh, uh, which does not contain uh, any ions in it, which means that it's going to be pure water. So the pH for pure water will be 7, and then for very alkaline solutions, the pH will be close to 14. Yeah. Very strong acids close to 0, very strong alkali close to 14. So in this case, we are going to introduce a new terminology here. Can you see it? Minus log base 10 of the Ka will be this unit which we are going to call pKa. Now, we are getting back to this equation here. Ka is concentration of the protonated water uh, multiplied by the concentration of the anion over the concentration of the parent acid. What you're going to see is that uh, the Ka or the Ka and the pH or the concentration of the protonated water, usually known uh, things which you can easily measure. There is an equipment which you can measure the pH. Yeah, there's an electrode which you can just put. You can put your substance. I mean your compound you are investigating. Then put this electrode and it's just going to tell you, oh, this is the pH. It's 5 or it's maybe 7 point something or close, whatever. So the pH can be known here. So there are two scientists called uh, uh, Henderson and Hasselbach. They did some rearrangement, and then they by just in this equation by putting water things which are known, the Ka and then the concentration of the protonated water uh, in one form, and then putting a logarithm scale logarithm here, and then putting a negative, so that you're going to get a negative for the pK for the Ka and the one for the water. Then you're going to, if you're going to do that uh, in these equations, I believe they can be seen quite well. Then you're going to rearrange to have this formula. Uh, Minus log base 10 of the Ka, that is the pKa, and this one is negative, and this, so I've just tried to rearrange here. If you're going to have something in the numerator and denominator, if I'm just going to open up this log, you're going to see that it will be the log base 10 of the one in the numerator minus the log base 10, the one for the denominator. So I'm going to get a negative because I've opened, but this one is negative. So it will be negative, but the one for the denominator will be also negative. So so this is the terminology: minus log base 10 of Ka, that is the pKa, minus log base 10 of the hydrogen ions concentration is the pH. So you're going to get this equation here. So this is called the Henderson Hasselbalch equation. pKa is equal to the pH minus log base 10 of the concentration of the anion over the concentration of the parent acid. Okay. So so you can be what you're going to see is this, and I need to mention it now. pKa, as you can see, it's given by the pH and then the concentration of the anion by the parent acid, this minus log base 10. What has been seen is that the pH minus the log base 10 of the concentration of the anion plus this uh, parent acid, that that number is a constant for a specific hydrogen in a molecule, or whatever it's joined to. So what you're going to say is that the pKa becomes a constant, just like the melting point, boiling point, maybe refractive index, and the rest. I would like to repeat: pKa is a standard variable for a specific hydrogen in a molecule. No other one is going to have similar pKa value. Are you okay with that? So this becomes a standard reference. And as a result of that one, scientists have been able to put pKa values as standard figures in an appendix, just like you can get the boiling points, melting points, and maybe refractive index and other things. Any common book on organic chemistry, organic chemistry, you will always see the pK values for various protons being put in the appendix. Yeah. So later I'll be referring you to this book, and I'm going to mention it later. That scientists have seen that the pKa tells a lot of information about electron density. The pKa tells very critical information about the electron density of certain protons in the molecule. Yeah. In fact, after this, you'll see a lot of things that we'll be talking about. After this, will be based on the pKa. In fact, uh, it's now become a very critical part of understanding a mechanism. If you don't know about the pKa of a certain proton which is being abstracted and the rest, you may not be able to understand about the mechanism. So what you're going to see, like in this book here, there are various. This is an appendix, like in this case. I hope you can see very well. And in this case, you can see it's written. Let me just try to see whether I can get it in focus. Good. Let me see whether I can get it in focus. It's written composite pKa chart. Let me see whether I can get it in focus. It's written composite pKa chart. So there are various protons there, and their pKa values, and there are about 3 pages. There's this page one, there are others and the rest. But once again, there may not be time for that one. Though I've actually put it in the course outline about understanding that one, and to really understand the the information which you can extract about the pKa regarding reaction and mechanisms, it can take 3 hours. Yeah, but once again, in the interest of time, and the problem is that such kind of things are not examinable. Yeah, so I may not focus on that one, but maybe later, maybe we may have time of revision. If you're going to have time, you can during like an online or like a face to face. If you're going to get time, you can be able to tell me, let's revisit this time this information about the pKa, and if you're going to get time, you'll really go to that one, and you're going to get to the information which it can give you about reaction mechanisms. So for now, just need to know this is the Henderson-Hasselbalch equation, and and the pKa is a constant for specific protons. Yeah, specific protons. Um, uh, okay, I think before I really go into that one, I think I may need to mention, which are going to be surprised. I don't know in the current book uh, uh, which page it is, because as I mentioned, the one which I've uploaded on the server is a newer version than this one, and therefore there's a lot of information which has been written, but for most of the information is quite standard for that. But one thing which I may need to mention is that which is being shown here. Let me just try to see whether I can get it. Let me see whether I can get on that. Okay, that is classification. Okay, good. I don't know whether it is possible to see very well. There is a summary over there. I don't know why it is not seen very well. Yeah, it's written summary here, that the pKa can be used for ranking the the strength of acids. By knowing the pKa values, you can be able to know, hey, this is a stronger acid, this is a weaker acid, something which you may not be able to know. For example, you're going to see that that hydrochloric acid and hydrobromic acid are much stronger acids than hydrofluoric acid. Yeah, even though the fluoride is far more electronegative than the chloride or the bromide and the rest. But once again, by looking at the pKa values, you can be able to know, hey, this acid is much stronger than the one. Rather than just trying to reason as to why this one is going to be stronger than this one, look at the pKa chart. It's normally a standard. It's normally included in all standard books on organic chemistry. So it can also tell you the ranking of bases. So you can be able to know you want to extract a proton so that you'll be able to know this is the base which I'm going to use. For example, you're going to know, maybe until now you may be thinking that the hydroxide, maybe sodium hydroxide may be a very good base, but you're going to see that it's one of the weakest bases. Yeah, sodium hydroxide is one of the weakest bases you can use for organic type of reactions. You're going to see there is something like butoxide, potassium butoxide, or lithium or sodium butoxide may be slightly more basic, but you're going to see there's something like uh, maybe something like lithium amide, but the best one, which is normally used for synthesis, is something like lithium diisopropylamide. It's called LDA. Maybe you've heard about it at undergraduate level. LDA, lithium diisopropylamide. It's got a pK of about 16 as opposed to this on the logarithm scale, as opposed to the sodium hydroxide. It's got a pK of about 15.7. So you're going to see uh, the LDA, it's like 10 to power 36 and 15, just like almost 10 to power 20 times a better base, far more stronger base than the sodium hydroxide. And then there are something like what if you can be able to use Grignard reagents, yeah, like what? If you can be able to form, like which one? I'm just trying to think of uh, stronger bases. Let me just try to look at this one. Like what? Uh, like if you are to get a proton from something uh, like if you had an alkane and then you had a halide, so you've got an alkyl halide, and then you use something like the magnesium to form a Grignard reagent, like maybe like uh, what a Grignard reagent like there is the I'm looking at Grignard reagents. Let me just try to delete the information on the board. I'm just trying to think aloud. Just a minute. Uh, Once again, I'll be able to, okay, let me just, because this one is a bit wet, let me just try to maybe clean it to be a bit dry. Just to give an example, I've got maybe like bromide, and then I've got a CH2, CH3. That's bromethane, and then I've got something like magnesium, and I'm using it in ether. In ether as the solvent, I'm going to get what? Uh, Mg Br CH2 CH3, so that this will be Mg2 plus, and then there will be the bromide minus, and then there's the CH2 CH3. Yeah? So there will be those ions. Yeah. So if you are to get such an anion uh, like the one from the alkane, which is deprotonated, these ones are going to have pKa values in the logarithm scale of approximately 50. So they're going to be a very strong, very powerful bases. But once again, all that information you'll be able to get from from this book. Once again, let me mention that once we are through with with what is going to be what is what uh, uh, what is examinable, then I think we can come to that which is said to be uh, for for your for your knowledge, but it's going to be quite critical. So the pKa can give information, as I mentioned, that was about the basis. It can also tell you something about the equilibrium constant. Yeah. Now this is now the most important information about the pKa, that what you're talking about, the equilibrium constant being the concentration of the products over the concentration of the reactants. In this case, you're going to say that you do not have to carry out an experiment to be able to determine the equilibrium constant. By simply knowing the pKa of what may be said to be the acid, and the one which is going to be the base which is subtracting the proton, there is an equation there which is being given by the equilibrium constant equals the log base 10 of the equilibrium constant is equals the pKa of the base minus the pKa of the acid. Once again, it is very simple like that one, and this thing is practical. It can be if you're going to do an experiment, you're really going to find about that one. So there is a lot of information you can find about the pKa, and once again, there is this book which I'll refer you to. It's on the Google Docs folder, and it's a very important book. You are really going to see that it's going to shape your knowledge on mechanisms about that one. So uh, uh, so there is this document about ionization of acids, which I'm going to send you via the WhatsApp, and it gives you strong acids and weak acids, and then later the derivation of the Henderson Hasselbalch equation, which is this one. The pK is equals to the pH minus log base 10 of the anion of the ratio of the anion of the anion which is produced from the ionization to the parent acid. And just to repeat once again, the pKa is a constant for specific proton in an organic molecule. Any proton you can think of, it has a specific pKa values, and therefore you can be able now to know if I'm talking about this proton, what you need to know is what atom is it attached to. And once again, I don't want to go into all those kind of things. Maybe later we'll come to that one. But in general, once again, in general, the protons which are attached to carbon have got very high pK values. The next ones are the protons which are attached to the nitrogen atom. Now, the ones which are attached to the oxygen atom are going to be lower, and then the ones which are attached to something like the heteroatoms, like the halogens, are going to have very low and probably even negative pK values. What does that mean? If the anion is going to very much stabilize, is going to be stable in solution, like for halogens like the chloride, fluorine, and bromine, then the hydrogen can easily go out as a proton, because it means that the anion which is going to leave will be stable. So the more stable the anion, the lower the pK value. And in general, like the ones for the halogens, those anions are going to be stable. They can be stable in solution. They're not going to react. Like for fluoride, chloride, bromide, and the iodide and the rest, yeah, are going to be stable. Then the anions like the oxygen, like for the hydroxide, uh, are going to be the next ones which are going to be more stable. Yeah. So those ones are going to have relatively lower pKa values. Yeah. And then the ones which are going to be based on the nitrogen, like the amine and the rest, are going to have much higher pKa values, because it means that the anion which will be formed as a result of the hydrogen migrating it's not going to be as stable as such. And the worst will be the ones the anions which will be formed as a result of the what of the carbon. Yeah. What you're going to see is that if you're going to have carbon, and then you're going to have alkyl groups like the CH3, CH3, and the CH3, like that one, uh, these alkyl groups are going to be donating electrons to the carbon atom by induction. Yeah. So you're going to see they're going to make this carbon more negative as a result of that donation. So you're going to see uh, rather than this anion becoming more stable, it's going to be much more unstable. All right. So the anions which are going to be based on carbon will be much more unstable, followed by the ones which are going to be based on nitrogen, and then the ones which are going to be based on oxygen are going to be more stable, and then the ones which are going to be based on the halogens like the fluorine, chlorine, bromine, and then iodine, these anions are going to be very stable. So the pKa values are going to be, yeah, other than for fluorine, the rest are going to be negative. Like this is going to be -7, -9, and this is going to be -10. Yeah. Are you seeing as a surprise that the hydroiodic acid is going to be much stronger than hydrobromic acid, and that is going to be much stronger than hydrofluoric acid? Yeah. No, hydrochloric acid, and then the least strong acid will be hydrofluoric acid. Yeah. It may be a bit of a of a surprise, but that's the information you're going to get from the pKa values. It's going to give you information about the stability of anions, like if you're going to form what like the inolate ions. So what you're going to see is that the anion which are going to be forming as a result of you abstracting that hydrogen, the information about the pKa values can actually tell you about the stability of that anion. And once again, if I'm going to explain all that, it's going to take 3 hours, and in the interest of time, because we are now as of this year of 2021, we're in mid-November, so there's not much time. I should mention this one requires proper 3 hours to really explain about the use of the pKa values in organic chemistry. So what is actually examinable about this? We'll see how the pKa can mention something. We'll be mentioning about aromatic compounds through something which we're going to call the Hammett equation. We'll come back to the information the pKa values can tell you about the mechanism. Yeah. But for the general ones, I'll just be mentioning it about it. But once again, I'll refer you to this beautiful book, Electron Flow in Organic Chemistry. To me, it's by far the world's best book on mechanism, Electron Flow in Organic Chemistry. It's by Paul H. Scudder, and in the Google Docs, this book, the latest version, is available. Yeah? So that one will give you information about that. And as I mentioned, uh, uh, I think there is there's a document I think I'm going to email you about the pKas and the mechanism. It's just like a short document, probably could be 5 or 10 pages, but that will show you how the information that you can get by looking at the pK values and looking at the various organic chemicals. I wish you had that on, but once again, in the interest of time, I think let me not go into that one. So uh, I think that's the much I'll talk about equilibrium, the pH, and the pKs. So in a short while, we'll get to what? We'll get to what do you call it? We'll now have a detailed look at the reaction rates. Uh, though I mentioned earlier, we're talking about zero order, first order, second order. What you want to do will be what? Uh, uh, to try to see how uh, you can be given experimental data, and then you can be able to use a graph paper or maybe Excel plot to be able to draw a graph and just say, if I'm talking about zero order, if I'm going to plot this concentration via time, then I'm going to get a linear curve. If it's first order, there's this kind of things, and if it's second order, there's this kind of things. And then sometimes you can be able to do some mathematics, and I'm going to give you information about the mathematics to be able to show uh, uh, the relationship between the concentration and the time if I'm dealing with either zero order, first order, and the second order. Yeah. So by that one, it will mean that you're going to make use of some some knowledge about calculus, the differential calculus, in which there will be the the rate of change of the concentration with time, and then we are going to rearrange to have the rate of the concentration of the of whatever is going to be changing relative to its parent concentration. You're just going to do some rearrangement on that one, and then eventually you're going to do some integration to be able to see between the time is zero to the time when the t is t, what the equation which you're going to get, and then we'll see what information you can get on that one. Yeah. So once again, there'll be some mathematics, but just basic mathematics. And the book which I'm really going to be encouraging is that one, Basic Engineering Mathematics. It gives you all the information that you need to know about mathematics from primary school, about addition, subtraction, algebra, trigonometry, all those things, introduction to the calculus, differential, and integration calculus, everything that you need to know about the mathematics that you need to know to really understand this course. Yeah. So let me stop there, and then we'll come to the proper coverage of the rates of reactions. Yeah. And then with that one, I think after that one, we'll be covering some other things which were left earlier. Uh, I think the one for the rate will go to slightly more advanced stage, because there's something to talk about the steady state approximations. Now that's the reason why we are talking about the equilibrium. What we are going to see is that there are certain equations in which you're not just going to have a plus b giving c. There's a way in which the a plus b can equilibrate to form an intermediate. That intermediate is going to form the product. So you're going to see how do you express an unknown in terms of the certain materials, and then make some approximations. What if the concentration of this is much greater than this? Then a certain numerator or denominator is going to cancel out, and then you're going to get a simplified solution. You're going to get to those things which you're going to be calling steady state approximations. Then there is the Hammond postulate, and then the Catenhammett principles, something like that. We're going to look at all those things which are left out, which were not covered earlier. So you are really going to come to that one. I'm really looking at the course outline, because at the end of it, you'll be able to say, have we covered everything as indicated in the SCH503 course outline? And then after that, we're going to be left with uh, two major topics, and that is the structure activity relationship, and then the molecular orbital theory, and alongside the pericyclic type of reaction. So those are the two remaining topics once you are through with the rest of the reaction. So let me stop there. I believe this topic about the equilibrium, the pH, and the pKa has been an eye opener to you, and once again, you refer to that book on electron flow in organic chemistry. It's the best book, to the best of my knowledge, on understanding mechanisms. On the Google Docs, there are other books on mechanism. I think there are about 3 or 4 in addition to this electron flow in organic chemistry. But once again, I recommend that book, Electron Flow in Organic Chemistry. Understanding the chemistry of the explanation on that, you're really not going to have a problem in understanding mechanism. So let me stop there, and we'll proceed after that. Yeah? Okay.